Now that we've characterized the cover inequalities, we need to start talking about the separation for the cover inequalities. Our separation procedure is only going to cover the basic cover inequalities. That is, these are cover inequalities that don't involve any extension or any lifting. Let's revisit exactly what the separation problem is. We're given a feasible region X, a polyhedron P, some feasible point X star inside of P, and we're going to assume in this case that this is not feasible for the region X. And we're also given our set of inequalities. In this case, we're given the cover inequalities. We can recall what a few of these things are. Our set of feasible points X is defined by exactly one constraint and allowing the xi's to be integers. Xi's are 0 or 1. The polyhedron P is the relaxation of this, defined by the same inequality, but now xi can take any continuum of variables between 0 and 1. Our cover inequalities are the basic covers inequalities. That is, we have the sum of the xi's inside of A is less than or equal to the size of A minus 1 for some cover A. Note that we can rewrite these cover inequalities as the sum over all the indices in our cover of 1 minus xi. This rewriting is going to be useful when we talk about the separation problem. The goal of the separation problem is to find one constraint, or at least one constraint in C, our cover inequalities, so that X star violates C. The alternative output is if we don't find some cover inequality that's violated by our solution X star, then we can verify that all the cover inequalities are satisfied. We're going to sketch the separation algorithm for cover inequalities. The basis for our separation algorithm is going to be the alternative characterization that we have of the cover inequalities. Namely, we're going to sum all the x's in the cover, 1 minus the xi, and say that's greater than or equal to 1. Our objective is to find some constraint inside of our capital C that's violated by our solution xi star. We can phrase this as finding some cover A so that the constraint is violated for our solution X star, where violation implies that the sum of the 1 minus xi stars over all the i's in A is less than or equal to 1. It's important to keep in mind two things when we're looking for violated constraints. First, the constraint has to be defined by a cover. That is, the sum of the constants inside of our set A have to be greater than B. In some sense, this is telling us that this is going to be a useful constraint, something that could potentially be violated. The second thing to note is although xi star seems to look like a variable, it's actually a constant. When we're thinking about finding a violated constraint, the variable that we're changing is A, not X. Xi stars are all given to us. They are the value of a solution. To find the violated constraint, we're going to introduce a knapsack problem. The variable in this knapsack problem is going to be Zi. It's going to be a 0,1 variable. A 1 indicates that the index I is going to be in our cover, and a 0 indicates that the I is not going to be in our cover. The objective function of our knapsack problem is going to be the sum over all I of 1 minus xi star. Our objective function is going to be the one side of the inequality that we'd like to identify, the violated inequality. The constraint in our knapsack problem effectively tells us that the zi's have to form a cover. That is, the sum of all the constants associated with a zi equal to 1 has to be greater than b. Note that this exactly defines the sum of the zi's that are 1 as a cover. To see how this knapsack problem actually finds the violated constraint, we first note that because the constraint is satisfied, the zi's that are set to 1 do in fact form a cover, and that our objective function, when it's minimized, is going to minimize one side of this inequality, since a violated constraint is going to only happen when this side of the inequality is less than 1. When this side of the inequality is at its minimum and it's less than 1, then we can be sure that it's violated. To be more precise, if it turns out that the minimum to our optimization problem S is greater than or equal to 1, then we can conclude that xi star satisfies all of our constraints. That's because the smallest that this can ever be is S, and S is greater than or equal to 1, and therefore all of our constraints are going to be satisfied. However, if S is less than 1, then we can conclude that the zi's are going to define a cover that's associated with a violated constraint. That's because exactly the sum over this cover of 1 minus xi is less than or equal to 1. And so we've identified the violated constraint. In this way, we've solved the separation problem by solving a 0-1 knapsack problem. Although this is useful in this case, it's also useful more generally. To develop a separation algorithm, one particular way to go about it is to identify some integer program where the objective function is one side of an inequality that we'd like to find a violated version of, and the constraints are there to define the particular set of constraints that we're looking at. In this case, our constraint tells us that we have a cover, and our set of constraints is defined by all of the covers.